Hello, welcome to the first in this series of webinars called Demystifying Scientific Cameras. This is part one and it deals with the fundamentals of scientific cameras. My name is Colin Coates and I've been a product manager with Andor for 20 years. Now, the reason we're going to have this series of webinars is that many people actually use scientific cameras in their day-to-day research, either used directly as part of their own built-up photonics setup, or sometimes, or in fact very often, they're within benchtop instruments. They are the key photonics component detector within benchtop instruments. They play a pivotal role, but actually very few people understand really what the fundamentals of scientific cameras are and what they deliver. But they're very important. They represent the ability to detect, resolve, and quantify your all-important signal. So that's why we're going to have this series, just to try and break down what some of the key parameters of scientific cameras are and hopefully make them that bit more accessible to you. Just to first set out an agenda for what we'll cover in these first couple of webinars on the fundamentals. First of all, we'll break down the different types of array detectors that we're going to cover. Then we will, in more detail, consider the concept of sensitivity and signal-to-noise ratio and why that's important for scientific detectors. And then to close out this first part, we'll talk about quantum efficiency as a key parameter of sensitivity and the various factors that go into determining quantum efficiency of detectors. Then, just as a preview for how we'll round up in part two, the second part of the fundamental series, we'll talk about signal-to-noise ratio in more detail and the various noise sources that go into determining the signal-to-noise ratio. We'll also cover the concept of dynamic range and digitization in scientific detectors, and then we'll finish up in part two with discussing field of view and resolution and resolving capability. Let's first consider the different types of detectors, photonic detectors that we can use in science. First of all, there's point detectors. So as the name suggests, these are not array detectors. These are single point detection devices designed to measure the intensity of incident photons versus time. Now, to their advantage, they're very fast. You can quite readily achieve sub-nanosecond time resolution from these types of detectors. So they're great for measuring dynamic changes of photon intensity versus time across a very, very fast time resolution domain. However, they're one-dimensional spatially speaking, and that means they're restricted to types of measurements very often that can benefit from that. They just need to measure changes in intensity but don't need to derive spatial information from them. Having said that, they can be adapted to spatial measurements, but it requires you to then raster scan across the image point by point to build up that spatial information content. An example being point scanning confocal microscopy then. A focused laser beam is put first of all on one point of the sample, intensity is measured from that point, then the beam is moved on to the very adjacent point in the sample, intensity is measured again. So if you do that again and again and again and again and again over many, many millions of points, you can build up in the end a high resolution image, but of course that is time consuming. But then you have actual array detectors, and that's what we'll be focusing most of our attentions towards. So you have charge coupled devices, the very popular CCDs. You have another form that we'll talk about in a later webinar called electron multiplying CCDs, intensified CCDs, and scientific CMOS. And we'll cover all of these to different degrees across a variety of training webinars. But fundamentally, across all of them, they're spatially two-dimensional. They tend to have very high quantum efficiencies as well, so that means they capture and convert the majority of their incident photons into measured signal, and they very often have the attribute of low noise floors as well. So they're generally, as a combined concept, very, very sensitive detectors. However, when you want to measure change versus time overall, they're relatively slow compared to point scan detectors. It simply takes longer to read out an array. Some are faster than others, and we'll discuss this at great length later, but suffice to say, compared to a single point detector, when you're only measuring 1 point fast, these tend to suffer in that regard. It just takes longer to read out an array. So the array detectors we're going to talk about are all based on silicon semiconductor. Now this is a very useful material for use in detectors. And basically when an incident photon hits a silicon-based pixel, there's quite a high probability that that photon will be converted to what's called a photoelectron, which is basically signal. It'll be then harnessed and converted to readable signal. Now a very useful property is that when charge is generated, it is generated proportional to the intensity of light that's incident on the pixel, which fundamentally makes the detectors quantitative. Now there's many more tricks we have to play in the scientific cameras to ensure that that quantitative nature is done very accurately and across what's called the full dynamic range of the detector with great linearity. But nonetheless, this is a fundamental property which we take advantage of. So let's first of all consider CCDs, or charge coupled devices. So there are three different array types that we're going to consider here. They're called full frame, frame transfer, and interline transfer. Now, they all have the common attribute that they're array detectors. They're sensitive to light. They convert photons to electrons. And they all get read out, i.e. the charge is transferred off those detectors. It's converted into a voltage signal and then converted into a digital signal, which you'll then read on your computer that the camera is connected to. Now, the differences between them are really about how the charge is transferred off the detector, off the array. So we'll consider these in more detail now. So let's first talk about full frame CCDs. And let's use a very common analogy that's often used in the context of CCDs, which is to consider that each pixel is a bucket and the photons become raindrops filling these buckets. So let's use that analogy to talk about how charge is transferred off these arrays. So we have this structure, this shielded structure down here, which in this analogy is a row of empty buckets. It's called the serial register. So to get the water from the first row off the array, it transfers its contents into each of these empty buckets in the serial register. And then bucket by bucket, they're transferred into a calibrated measuring container. So to leave the water analogy for a second and move back to the CCD, that's really referring to this output reading architecture here, which is really a means of converting the charge and electrons into a voltage signal, which is then digitized and then becomes a signal which you then read on your computer. But this happens in a very serial fashion on a full frame CCD. So every pixel in the first row is then sequentially transferred into this measuring container, the measurements made and then emptied, and then the next one is transferred in. So this is a very time consuming process. So the first row has to be done like this, then the next row is moved along, it has to be read out pixel by pixel also. And so that is relatively time consuming, but that is full frame CCDs. Now, just a couple of other points to make about them. To their benefit, you can get them both front and back illuminated. Now, we haven't really talked about front and back illuminated structures yet, and we'll do so in a few slides, but bear that in mind for now. It can be one of the strong advantages of full frame CCDs in that they can be back illuminated given the highest possible quantum efficiency. So they can be very, very sensitive. They're, however, slow readout. To keep the noise low, and we'll talk about this in more detail later as well, you have to read them out relatively slowly. So again, it's not for fast measurements by any means, and they require a mechanical shutter. So for imaging, that is. So because of the nature of this pixel by pixel charge transfer during the readout and it being relatively slow, you can't have light falling in this active area while this charge transfer process is occurring. Otherwise it will result in some vertical smearing. So you have to close a mechanical shutter over the active array while this readout is happening. Now, for many applications that's okay. For some applications, mechanical shutters are more undesirable. So let's consider now the frame transfer CCD. So fundamentally, it's really quite similar to what I just described for full frame, except it has the addition of this fully masked light shielded storage region. So this is really a mirror image of this active area here, except it has a mask shield. These pixels are shielded from light. Now let's talk through the sequence of how these frame transfer CCDs work. So step one, before the exposure begins, all the charge that's being collected in this active area is being continuously swept down into the shielded area from where it is read out and basically just gotten rid of. That's the way of keeping this active area clean and free of charge without needing a mechanical shutter to be closed before the exposure starts. So it's a very fast process, very effective at keeping charge purged from this light exposed area. Then we want our exposure to start, so we stop doing that cleaning activity. We just let the charge build up from the incident light, and that's what's happening in step 2 here. Now step 3, we're saying this is the end of the exposure, and this is really quite novel to frame transfer. What happens now is the entire image is very rapidly shunted down into the masked area, the readout area. This happens very, very fast, to such a degree that it rarely results in any vertical smearing, because it's a very fast process relative to the time taken to build up the exposure itself. Now, and this is where it gets really quite interesting for frame transfer CCDs, because you have this capability now to immediately start exposing your next image while you're simultaneously reading out the previous image. So there's no time wasted here at all. This is what's called a 100% duty cycle. No photons are wasted, basically. We can immediately go on and start acquiring the next image while the previous image is being read out. And the readout sequence is just like I described for full frame. It's pixel by pixel, row by row, in that fashion that I described, using that bucket analogy. So once that's done, we then go through the process again. You take your second image, you transfer it into the image area and read out. So that carries on and on and on throughout the whole kinetic series of your acquisition. So the advantage is it can be a faster process, and you don't need a mechanical shutter, which for some applications can be advantageous as well. Again, this can be back, the sensors themselves can be back illuminated to have higher quantum efficiency. So that's very much an advantage of the process also. So finally, let's consider interline CCD architecture. Now, interline CCDs are not nearly as common as they were 5 to 10 years ago. They used to be very, very common, especially in applications like fluorescence microscopy. But in fairness, they've been largely replaced by scientific CMOS these days, but they do still exist to an extent, and we should cover them to properly understand them. So they are very similar in a way to frame transfer CCDs that I just described, in that for every pixel you have a masked area into which charge is transferred. So if we look at this diagram here, we have, for example, this active pixel area, and then right beside it we have a masked area for that specific pixel into which this charge can be transferred. So once all the pixels have simultaneously transferred their charge into the active masked area, the readout can begin. So for that to happen, it then happens very similar to what we described for full frame CCDs. The charge is transferred into a readout register, and then pixel by pixel, that charge in the readout register is read out into this output architecture, the readout architecture. So it happens in a serial fashion, just as you would expect for a CCD, but just like the frame transfer advantage, while this readout's happening from the masked area, you can then begin to acquire your next image in the light active area of the pixels. So again, you have this 100% duty cycle advantage, which translates into a speed advantage and the fact that no photons are wasted. You're immediately going from one image into the other. While the second image is being recorded, your first image is being read out from the masked area. So there's some pros and cons. Again, it's a faster technique because of the 100% duty cycle, because the transfer of charge is very fast, and into the specific masked architecture, we again avoid the need for a mechanical shutter. But in this case, actually, interline CCDs are not amenable to back illumination, so they have more restricted quantum efficiencies. We have to actually use micro lenses on top of the array to channel more of the photons into the active area of each pixel and away from the masked area of the pixel. So that does, to a large extent, increase the quantum efficiency, but not to the same extent that you would have with back illumination. And again, we'll talk about this in more detail later on, but that's interline CCDs. So before we move on from CCD architectures, I just wanted to describe this interesting little mode that we've put into all of our CCDs and EMCCDs, and our calls it fast kinetics mode. And it's a way to basically, despite the fact that CCDs, as I've said before, are distinguishable by having relatively slow time resolution, this is actually a way to derive microsecond time resolution from otherwise slow readout CCDs. And it does that by using the microsecond time resolution of vertical shifts during readout effectively. So I'll try to describe what's going on here. Basically, we're defining a very small region of interest at the top of the sensor. I'm using here an architecture of a frame transfer CCD, but this could equally be done with a full frame CCD. So we have to optically shield the rest of the sensor from light falling on it. So say we've allocated, and you can do this through software, for the sake of argument, 50 rows at the top of this active area. We have to make sure that the rest of this area is optically shielded from photons, because don't forget, this strictly speaking is active area. As far as the sensor is concerned, it's open to photons, charge can be collected here. It's up to us in the experiment then to make sure charge cannot be collected here. So that's where optically shielding of the rest of the sensor becomes important. So then you record, you acquire your image in the, say, top number of rows, and then once that's done, you do a vertical transfer of the image into the 40 rows beneath that. Again, this happens very fast. Vertical parallel transfers happen on typically on a sub-microsecond to say up to say 10 microseconds per row timescale, depending on the sensor type, but very fast dynamics irrespective. And then immediately the next image is acquired. And so you do that again and again and again in a burst until the entire array has been filled up with successive images. So as a consequence, you've managed to obtain microsecond order time resolution from a CCD. But that's the thing, it's burst kinetics, it's not sustained. Once you have filled up your array with these images, you then have to do a slow readout, a relatively slow readout, as you would for a standard full resolution image. So that's fast kinetics mode. So let's briefly touch on the fundamental difference between the readout of a CCD versus that of a scientific CMOS. So we've already described CCD readout in reasonable depth, but it's defined by this row by row, pixel by pixel serial readout nature, and therefore it's relatively slow as a consequence. CMOS or scientific CMOS, in direct contrast to that, is highly multiplexed, highly parallel in its readout mechanism. So on each detector type, the photon to electron conversion takes place at the pixel. We've already described in silicon semiconductors, an incident photon gets converted into a photoelectron. That part's similar between each architecture. It's the nature of where the charge to voltage conversion as part of the readout process occurs. On a CCD, it occurs in the one common output structure. So every pixel is transferred in serial through this common output structure for charge to voltage conversion. But on a CMOS, it happens at the pixel level, and that's the key difference. That's one of the bottlenecks of imaging, taken care of at the pixel level, rather than a common output architecture of a CCD. That makes it highly parallel, but by contrast, and generally makes CMOS imaging that much faster than CCD imaging. So I'm not going to go into a lot of detail here, don't really want to in this fundamentals type webinar, but hopefully that gives you an idea of why CMOS frame rates are typically much higher than CCD frame rates. Now, you might ask, why doesn't everything just go towards CMOS? Well, and again, we'll cover this on a different webinar in much more detail, but because of this idea that charge to voltage conversion happens for every pixel individually, there is more variability in the quantitative nature of CMOS compared to CCDs that you then have to correct for at the camera level. But it's never truly as fundamentally magnificent as it is for CCDs. CCDs, because they all go out through a common architecture, are very uniform in their image qualities and in their quantitative nature. You can do a lot to improve CMOS, and we do, especially in scientific CMOS, to make them as uniform and parallel and homogeneous as possible. And a very good job is made of that, but CCDs will ultimately have that fundamental advantage. Everything is sent out through a common architecture. It's pretty much as homogeneous and uniform as you can imagine. So let's turn our attention to the concept of sensitivity. I mean, this is very fundamental to scientific digital cameras and distinguishes them from standard, high street digital cameras, or from the cameras in our cell phones. So the reason we don't use the camera in our cell phone, and they are, to be fair, getting more and more sensitive, but the reason we don't call them scientific detectors, one of the key reasons, is that they lack sensitivity. A lot of scientific applications simply need sensitivity, and here are some of the justifications. It's not an exhaustive list, but it typifies why different types of applications would demand that higher level of sensitivity from cameras. So especially in biological imaging, you might have a need for low dye concentrations or low fluorophore concentrations, and that goes right down to the very level of the single molecule. There's a whole area of fluorescence microscopy dealing with single molecule dynamics within the area of biophysics. But in live cell imaging, for example, we don't want to completely overload living cells with fluorescent dye. It can actually affect the physiology of the process that you're trying to observe. So we want to keep those dye concentrations as low as possible, but with low dye concentrations comes a proportionally lower signal level, and therefore we need higher sensitivity in our camera to counteract that. Shorter exposures and fast frame rates go hand in hand. Sometimes we just want to measure things that are very dynamic by nature. We use then a faster frame rate mode and therefore shorter exposures to achieve that. But again, with a shorter exposure, you're simply not collecting as many photons as you would be with a longer exposure. Again, we need to counter that with higher sensitivity. High photon loss and photon rejection. What I'm really getting here are the modalities of imaging, such as confocal microscopy, where there simply are a lot of photons from the signal rejected. In confocal, it's the trade-off between confocality, getting as thin of a sliver of the sample imaged as possible in the z direction, versus signal to noise ratio. So we're simply rejecting a lot of photons in a confocal configuration, and it's inherently a very low light signal. Therefore, again, it's ideal for sensitive detectors. Lower excitation power is a very important one, not just in fluorescence microscopy, right across scientific measurement, chemical and materials. Very often we don't want to damage a photosensitive sample. That can be in biology or chemistry. But again, using the concept of live cell microscopy, low excitation powers are absolutely fundamental. We want to keep our living cells alive as long as possible. Too high of a photon flux exciting your cell will actually kill the cell through phototoxicity prematurely. We don't want that happening. We want to keep these living cells alive for as long as possible. It can also bleach the levels of fluorescent dye that you have in the cells, and again, that's undesirable. So with lower excitation power, as you might imagine, fewer photons in means fewer photons out on the emission side, and therefore we need to counter that with greater sensitivity. Greater magnification. So what I'm getting at here in any imaging setup, if you have a higher magnification, you're taking an amount of photons is coming from a defined area of the sample and spreading that over more pixels of the detecting array. So any one pixel will receive fewer of those photons. And again, you need greater sensitivity to help with that. And then sometimes through the nature of the science of what we're doing, you're just confined to imaging or measuring something spectroscopically, for example, a material that just simply has a low quantum yield of emission. And if this is Raman spectroscopy, for example, Raman scatter by its very nature is weak. There's ways to enhance it, but fundamentally Raman scatter is a weak phenomenon. So again, this all needs a highly sensitive scientific detector to make sense of. So let's talk about, at a very basic level, the fundamental parameters of sensitivity. So one that's quite often understood is the quantum efficiency. And this refers to how effective the detector is at catching incident photons and converting them to electrons. And we'll talk more about quantum efficiency in 1 or 2 slides' time. And the other one, which is more often overlooked, but it should not be because it's very, very fundamental to the whole concept of sensitivity, is the noise floor. I'm using the analogy here of an object sitting in grass. So basically the noise floor is your grassy detection limit, if you like. If your object is completely buried by noise, or in this analogy, longer grass, you simply won't see it. So to make a detector sensitive, we really have to have a strategy to overcome that noise floor. And we'll talk more about that later on in this webinar. But for a sensitive detector, you really have to have both of these parameters optimized as much as you can. You have to have high quantum efficiency to catch as many incident photons as possible, and you have to cut that grass, get that noise floor down as low as possible, such that any photons you do convert to electrons will be seen, won't be buried in a grassy noise floor. So let's talk more about this concept of quantum efficiency, first of all. So quantum efficiency is represented by plots. It plots the spectral range of detection. I'm showing here quite a full range from 200 nanometers up to 1200 nanometers versus the quantum efficiency as a percentage on the y-axis. So say we had something that was 80% quantum efficiency at around about 600 nanometers. It means if 600 nanometer photons are falling onto a pixel, on average 80% of those incident photons will be converted into photoelectrons. That's simply what it's saying. So obviously the higher and broader the quantum efficiency, the better the detector. So what we're doing in this slide, without going into any great detail, is showing some typical quantum efficiency curves for a range of different types of detector, of CCDs in this case actually. We have front illuminated here with a relatively low quantum efficiency, and we have some other types of detectors here that are all back illuminated, and we'll go on to the reasons why these curves might differ in future slides in this webinar. But suffice to say, back illumination tends to deliver high and broad quantum efficiency, but as a concept tends to be more expensive than front illuminated. So let's talk about front illuminated versus back illuminated detectors. So in front illuminated detectors, you have an architecture like what is represented here. Where the light is incident, you have an electrode structure. Now the electrode structure on the front surface is needed. There's no doing away with electrode structure. It's needed to contain the charge and to do your readout process that we talked about earlier. But unfortunately, it impedes the passage of some of the photons through to the active silicon area that you really want to get them into. So the active silicon area here is called the depletion region, and it's this darker gray layer. Now, that's really where we want the photons to get to. That's where they get converted into photoelectrons. That's where the signal collection happens. So we want the photons to get us past as much of this electrode structure as possible and into this depletion area. But as I said, front illuminated just inherently has that drawback. It impedes the passage of some photons through the electrode structure. So that's why there's been an alternative strategy developed called back illumination. Basically, we flip this front illuminated structure 180 degrees. We turn it upside down. Now, unfortunately, you have this additional structure called bulk silicon, which is undesirable for signal collection, and we want to get that thinned down. So that's what happens here. There's an etching process which is used to thin down as much of this bulk silicon as possible until you're basically left with the sensitive active depletion region of the silicon right there exposed to the light. So the incident photons are unimpeded, going straight into the active silicon, and you get the greatest collection of photons, the greatest capture rate of photons, the greatest probability of converting a photon to an electron. So that's basically what happens. This etching process is not easy. It's not a trivial thing to do. There's only a certain amount of places can do it around the world. The yields tend to suffer a little bit as well in the fabrication process, and it therefore means that it drives up the cost of the process. It means back illuminated sensors are typically significantly more expensive than front illuminated sensors, which drives up therefore the end user price of the scientific camera when it is back illuminated. But if you want the broadest and highest quantum efficiency possible, then back illuminated is the answer. Now, just to bring this concept a little bit further, very often applications are increasingly concerned with enhancing response in the red and the near infrared wavelength region. So if we look again at the back illuminated architecture of a chip, what we have here is a thicker depletion region. So remember, this is the active area, the active layer that photons are trapped in. When this is relatively thin, more of the near infrared photons will just pass straight through it without being absorbed and converted into an electron. Therefore, by simply increasing the path length through which the photons have to travel, we collect more of those near infrared photons in this depletion region. So these are more expensive again. It's a more expensive process, but it's increasingly popular to have deep depleted CCDs, especially for applications such as astronomy, where near infrared detection really is becoming quite important. Even in the biosciences, there's more and more fluorophores being developed that emit in the near infrared wavelength regime, with various benefits. It helps you penetrate deeper into samples if you're using near infrared dyes, for example. This can be less damaging to samples as well. So there are increasing levels of scientific justification for enhancing near infrared response, and this is a key way to do it. Just to show you some of the benefits of this deep depletion process, if we look at what's called the BV curve, this green curve, that's a standard what's called mid-band back illuminated profile. optimized very much for this 500, 600 nanometer wavelength regime. However, if we do deep depletion, you can see it optimizes the region around, say, from 700 out to 900 nanometers. So it's much, much better at collecting photons in that wavelength regime. Out of interest, I'm also showing some curves on this plot called BU and BU2. These are actually blue and UV optimized curves. I'll not go into the specific process behind them now. It uses what's called an enhanced silicon process, and it's combined with special anti-reflection coatings which are optimized for the blue and UV as well. But it's just to say that you can actually get curves optimized for blue and UV regions should that be desirable. Now, finally, it's not always practical or affordable to have a back illuminated solution, and one option that's often used for front illuminated devices, including scientific CMOS. The majority of commercial scientific CMOS sensors in use in the scientific market today are front illuminated, and they use microlenses. So microlenses is simply an array placed in front of the active silicon array, which for each pixel has its own microlens, which is designed to focus the photons into the active area of each pixel. So it's especially important in CMOS. As it happens, there's plenty of structure on the front side of a CMOS device that can impede the passage of electrons. So it's especially important to be able to focus light into the active area and away from this structure which would otherwise impede the photons. So it does enable some very high quantum efficiency actually, and it's less expensive than back illumination. It needs to be approached with caution for some applications more than others though, and it's because there's a sensitivity of the quantum efficiency to basically the angle of the incident light on each of these microlenses. So they're really designed to be optimal when the light is close to parallel. And actually in microscopy, this is more or less the case. So it tends to be not a concern for microscopy. But when light is incident on the microlenses from an optical system which has quite a low F number, or you can see the cone angle of light is coming from all directions here, then you'll see that some of the photons do actually get impeded by the electrode structure, and so the microlenses are basically less effective if the light is not coming from a parallel incident direction. This is a problem you don't have with back illumination. No microlens means that you can use a greater sweep of F numbers of incident light direction, and the photons will not get impeded. So it's just something to be aware of, and it can be more important for applications like astronomy, where some telescopes can have quite low F number incident light. So I mentioned the quantum efficiency actually can be very high. This is a really good example. They're not all this amazing looking, but this is one of our scientific CMOS cameras called the Xyla 4.2 Plus, which uses a microlens enhanced front illuminated SCMOS. And you can see here we're getting about 82% peak quantum efficiency. So I'm comparing that here to a back illuminated CMOS from Andor's range called the Sona 4.2. And that's, of course, as I described, high and broad quantum efficiency. But for a front illuminated response, this really isn't bad at all. 82% is, really quite within reach of what is being achieved by, a more expensive back illuminated approach. So certainly for many applications, this will do the job. This will absolutely do the job in a very cost-effective manner. So in order to break this into more bite-sized chunks, we're going to conclude part 1 on the fundamentals of digital scientific cameras right now. But I urge you to continue the journey with the part 2 in the series, where we'll cover more concepts like signal-to-noise ratio, noise sources, dynamic range, digitization, and field of view and resolution. Thank you very much for your attention.